Hey, this is Horner, and this is Energy and Work, Conservation of Energy and Work, Part 4. And we're going to take a look at some energy diagrams to begin with. So remember, if you have a graph showing a system's potential and total energy as a function of position, we call that an energy diagram. And you've done a lot of energy diagrams already if you went ahead and went back and did those worksheets again. When we look at the energy diagram, the distance from the axis to the PE curve is the particle's energy or the potential energy. The distance from that PE curve to the TE line is the kinetic energy. So the PE curve to the TE line, that's the total energy, so you'll see it down here, is the kinetic energy. So they're transformed. We know that as that position changes, so as something falls, it picks up kinetic and loses potential, causing that particle to either speed up or slow down, but you'll notice that the sum of the two energies never does change. The particle can't ever be at a point where the PE curve is above that TE line. So where the PE curve is above the TE line, the particle can't be there. So it's got to be in this area down underneath. So hopefully you'll see that. Oops, yeah, I do want to delete that. Okay, the PE curve is determined by the properties of the system. So we think about the mass, the spring constant, all those different types of things. So we can't change that PE curve, but we can raise or lower the total energy by giving the initial conditions so that things have more energy. So for example, if I have a particle here, if I raise it up, I've increased the total energy of the system. If I start it down here, I've decreased the total energy. So you just have to be very, very careful that you're conserving energy unless it is a non-conservative system. Minimum PE curve is the point of stable equilibrium. So that's basically where you're just going to have everything's going to work out. A maximum in the PE curve is a point of unstable equilibrium. So that's where it's got a lot of energy and it's just it's getting ready to release all that energy. So you can kind of see what happens here with this particle in free fall, and notice that it does go up first and then it falls back down. So you're looking at where this is. Notice that it's at the very bottom on the curve. It's very stable there. As it increases its energy, it becomes more unstable until it has total potential energy. And then when it falls back down, it's coming back to a state of equilibrium that it enjoys. This graph is a little bit different because this one is for a spring. So you'll notice that the curve has changed. In the previous one, remember that potential energy, so UG, due to gravity is equal to mgh. So for these, all the curves are linear. So you'll see that as my height increases, my potential energy increases linearly. And so that is your relationship between the two. If we move down here, remember that potential energy in a spring is equal to 1/2 kx squared. So anytime that your stretch or compression go up, so we've got stretch and we've got compression, you'll see they go in opposite ways. We have a parabolic function or a quadratic function. So parabolic curve, quadratic function. Springs and energy conservation, this is a really important topic. This is something that they do a lot on the AP Physics C exam. Just because of the quadratic function, it's not as simple, and so they're going to use it more often. So in springs, we are both transforming that energy back and forth between both kinetic and potential. So when it's fully stretched or extended, then all the energy is potential. So you'll see that this one is compressed. So this one is compressed and this one is extended. So either way, we have all potential on those ends. And then here we have just an equilibrium condition. So at all the other points, other than right here at equilibrium, it's a mix of both U and K. So in between this line and this line, we're going to have both U and K. And over here, same thing. Between the 2 points, you have U and K. But right in the middle, it's all kinetic energy. That's where the spring is totally relaxed. So all the energy is now tied up in speed. If we move on, this is all about system energy. And we know that conservation of system energy basically just says that we have the potential energy plus the kinetic plus any internal energy, and that's thermal energy. So that's the energy of friction, of heat coming from that, and that mechanical energy can be converted to and from heat. So if you add heat to a system, you're doing work on the system and it gets more energy. If you take heat out of the system, then you lessen the energy. So here we kind of see what's happening. We know that work done on a system puts energy into the system. So if you think about some of those bar graphs that we've done, sometimes you'll have work going into a system. So your potential energy due to gravity, potential energy of a spring, kinetic energy, rotational kinetic energy, this is translational. There's no bar graph here. Everything's flat because we have work going in. When you have work going in, so maybe you lift something, then that gives you all potential energy due to gravity, no spring, no translational kinetic, and no rotational kinetic. So that's what the bar graph would look like on the other side. If work is done by the system, then we have energy coming out. So if you just make this go the other way, so it's going like this, then that work is going to be coming out of the system and coming back. So that's kind of what you'll see as it goes through. So notice that this potential energy to gravity, let's say that it doesn't translate into kinetic energy. Instead, there's work done. So you don't see that work. You see the work coming out, but you don't ever see the object or the system move. So here, this is important. When work is greater than zero, the environment does work on the system, and the energy increases. When work is less than zero, so basically that's just saying that your work is negative, then the system does work on the environment, and the system's energy decreases. So it goes down. That kind of will help you remember why it is negative. Work is defined in your equation sheet. You'll see it as FD cosine the angle. You're also going to see another equation for work, and we'll go through and we'll derive that equation here in a second. So the unit of work is a joule. So remember that would be a Newton times a meter, which is equal to a joule. We also could say that that is a kilogram times a meter per second squared times a meter, and that is equal to a kilogram times a meter squared over a second squared. So just some units that you should probably get used to. Forces can do positive, negative, or zero work. So when you push a box on a flat floor, for example, the normal force and gravity don't do any work because they are equal and opposite, and they are perpendicular to the direction of motion. The person pushing the box does positive work since they're pushing in the direction of motion, and friction does negative work because it's working against the system. Do remember that work does change mechanical energy. So work is sometimes defined as the change of potential energy and sometimes defined as the change in kinetic energy. If you apply a force and it does positive work on the system, it tries to increase mechanical energy. If an applied force does negative work, it decreases. So remember, this would be friction, and this would be some sort of applied force. The two forms of energy are called potential and kinetic, and there are lots of different types of both as you go through. This is where we're going to work on just a little bit of calculus. We're going to do basically the same thing that we've been doing this entire unit. So here we've got a force. It is working on the particle, and it is moving it from an initial position, SI, to a final position, SF. It has no kinetic energy at the beginning, or has very little, and as we apply that force, then we increase the kinetic energy. So do remember that the force may vary in magnitude and or in direction, and because of that, remember work is equal to force times some sort of change in position times the cosine of the angle. So if your angle is 90 degrees, notice that no work is being done because the cosine of 90 is 0. If the cosine is 0, then there is a full amount of work being done because the cosine of 0 is 1. Let's go ahead and take a look at the calculus. So we're going to use calculus to come up with an equation, just as we've done before. And so what we'll do is we're going to start down here. We know that the force in the direction s, so that's just like x, is equal to mass times acceleration in that direction. And as we've said a million times before, that is mass times dvs over dt. We're going to use the chain rule now, and you should be used to the chain rule. So we know m dvs over dt. And so here we're going to say this is mass times dvs over, and then we're going to do ds. So remember, as long as we multiply the bottom and the top by ds, then we can do this for the chain rule. Our ds over dt becomes vs, so this is m vs times dvs over ds. So we took this, and because it's change in position over change in time, that is velocity, and that is where it goes. So now let's rewrite our equation that we have up here. So this is Fs is equal to mass times the velocity times dvs over ds. So notice they're different, dt here, ds here. And why? Because we were able to use the chain rule. At this point, what we're going to do is we're going to go ahead and put in both sides of our equation. So now we have m vs d vs is equal to the force in that direction times the distance, or ds in that direction. So how did we get this? Remember, we multiplied both sides by ds. So we're going to multiply this side and this side by ds, and when we do that, we end up with work. And so force is equal to ma. Ma is equal to mdv over ds. It's also force is also equal to m vs dvs over ds. And so if we multiply this force, remember this is force, times ds, we get work. So there's our force times ds. And when we do this, notice that the ds on this side cancels. I know I've switched sides. I'm really sorry about that. We need to go through and do our integration now. So let's do that up here. So we're just going to move on up here. And we've got mvs dvs. And we're going to integrate. And remember, on this side, we're going to go from our original velocity to our final velocity, because that's what we're integrating, is the vs. And that's equal to 1/2 of mvs squared. And we're doing that going from that final velocity to our original velocity. So we're just doing this side of the equation. I should have mentioned that beforehand. So we're just doing this side of the equation. And so when you go through and you actually plug everything in, this is 1/2 of mvf squared minus 1/2 of mvo squared. So we put in vf and vo for our vs. The other side of the equation, when we integrate it, remember we are not going from v to v, we're going from so to sf, and this is fs ds. When we integrate it, we're going to end up with work. Oh, interesting, right? So here we've got the change in kinetic energy on the left, and on the right we have this guy. So this, remember, is equal to change in kinetic energy. And so because this is equal to change in kinetic energy, and it's on the left side, and this is equal to work, and we know that work is equal to the change in kinetic energy, we can say work is equal to the integral of Fs ds. And we're looking at that from any position to a final position. And that is the calculus equation for work. Let's kind of see how that works. Sorry, no pun intended. But let's move on down to the next page. So this equation gives us a specific method to calculate how much energy is transferred by a push or a pull. So that energy transfer by mechanical means is what we mean by the term work. So now you should have a better idea of what work is. The work energy theorem is what we just went through and did the derivation for, and it just means that the net work is equal to the change in kinetic energy. So work due to all the forces acting on the object is the F net, and the change in kinetic energy is just Kf minus Ki. So whenever you have one or more forces acting on a particle, And remember, this has got to be acting parallel to the particle. It can't be acting in a perpendicular fashion. Then the net work done on the particle by those forces causes that particle's energy to increase or change, so maybe go up or down by our equation. So if I want to actually do some things with this and calculate the work, I can just kind of take a look very basic at this and notice that if I have a force acting and that force then decreases from our 5 meter to our 10 meter point here, you'll see that I've done work is the shaded area here plus the shaded area that I have here. So here I've got a constant force, and here I have a non-constant force. So this is just a particle moving along the axis in this figure, and the force vector, so you'll see my force vector, makes an angle with respect to the displacement. So this angle should be angle theta here, so we'll change that. So the component of the force vector is the F cosine of the angle. So that's where that cosine comes from. So here's our equation modified where we had Fs ds. Now we have F cosine of the angle in relation to that change in position. So both F and the angle, so this should be angle not Q or constant, so they can be taken outside of the integral. So what we're going to end up with is this. Work is equal to force times the cosine of the angle, and then we're going to integrate from SO to SF, and we'll integrate ds. So this really is equal to F times the cosine of the angle times SF minus SI. So remember, S is your position. So our work now can be equal to force times that change in position. So we're going to put delta R there. Don't think of that as a radius necessarily, but you can. And then that's times the cosine of the angle. Be careful here. Remember, delta R is equal to SF minus SO. And that is the section number 4 of going through and taking a look at what's going on in terms of work and conservation of energy.